Apple II wire-by-wire build, video circuit, vertical sync. I'm Dr. Matt Regan. In the last video we generated the horizontal sync signal, and in this video we're going to go over the vertical sync. Here's a cross-section of a cathode ray tube. These were commonly used in the era of the Apple II to display the image. At the back we have an electron gun, which is a heated filament that produces free electrons. The electrons are accelerated towards the screen. The front of the screen is covered with phosphor. Then when the electrons hit the front of the screen, it glows. Now importantly, these monitors have these little deflector coils on the side, and they generate a magnetic field that can bend the electron beam. So, with some clever electronics, we can sweep the electron beam all over the display. We'd start at the upper left, move to the upper right, then we'd quickly scoot back to the left and down a little. This is one scan line, and we'd repeat this pattern from top to bottom. This type of scan is called a raster scan. Here's a typical scan line for the Apple II. It has 65 characters, and each character is 7 pixels wide. The exception is the last character, but we'll worry about that a bit later. There are 40 active characters, and we use 4 characters for sync. Then there's a region called the front porch and the back porch, which are usually blank. Then we built this circuit, which counts through the characters and generates the horizontal sync signal. But now...
He's going vertical, so am I. We're going ballistic, man! Go get him!
The Apple II has 262 scan lines per frame, and this is based on the NTSC standard. 192 scan lines are active, and the remaining 70 are blank. Within that blank period, we use 16 for vertical sync. Now, many implementations have a shorter vertical sync than this, but this is what the original Apple did, so I'm just going to replicate it here. To build this, I need a binary counter that can count to 262, so I'm going to need 9 bits. This will take 3 of the 74HC393 counters, so 2 chips in total. In character mode, the first 3 bits of the count are used for the line position within a character, and so Steve Wozniak labelled these VA, VB, and VC in the Apple II. So I'm just going to stick with this convention. The next 6 bits are character row, and they're labelled V0 through V5, and I'll use these as well. To divide by 262, I need to detect the pattern 1 0 0 0 0 0 1 1 0, which is binary for 262. I told you binary would come in useful at some stage. The counter starts at 0, and I reset it to 0. So I really only need to detect when VB, VC, and V5 are all high. I don't actually really need to check all the others for zeros. If this isn't clear, have a think about this for a moment. I can use a 3-input AND gate to detect when all of these signals are high together, and when they are, I just reset the counter. And there we have it, division by 262. Now I need to generate the vertical sync signal. Ideally, I'd like to place this at the center of the blanking period, but if I do the math, this occurs at line 219, so instead what I'm going to do is move the vertical sync signal down to 224, which is Z0 in hexadecimal. This will make the vertical front porch a bit bigger than the vertical back porch, but I'm willing to live with that for the moment. By doing this, I need to detect the pattern 1110 on lines V4 through V1, and this is much easier to do. So here's the circuit for doing this. I'm going to use a large 8-input NAND gate, just in case I want to move the vertical sync signal around a bit. Note that in this case the vertical sync will be active low. I like to use KiCad for schematic capture. It's free and it's easy to use, and there's an auto router available if you want to make a printed circuit board. This is showing at 6 times real time, but you can slow it down and look at the circuit in more detail if you like. I know many people watching this channel are visual learners, so I'm going to play some music while you do some visual learning. This is the signal V5, which has a period of about 17 milliseconds, which is what we'd expect for a 60 frame per second update. And this is our vertical sync signal. The scope's having a hard time locking onto it for the same reason I think it had a hard time locking onto the horizontal sync. I think there are a bunch of short transitories caused by the logic. It's only when I set the trigger voltage to be very low that the scope can lock onto it. It looks about a millisecond wide, which is what I'd expect for 16 scan lines at 64 microseconds each. Now that I have both sets of counters working, I can generate this 2D map of what we should see on the screen. The blue is the active area, green is blank, and the red are the sync signals. The next signal I want to generate are the horizontal and vertical blank signals. We'll start with vertical blank first because it's a little easier. For the first 191 scan lines, we want vertical blank to be low. Then from 192 to 261, we want it to be high. And we don't really care about the other regions. To help design the logic for this, I'm going to introduce the concept of a Carnot map. There are several good videos on the internet about Carnot maps, and I'll link one above. The idea is to identify these regions with either 1, 2, or 4 ones in them. We can count the x's as either 0 or 1, whichever makes the circuit simpler, but it has to be a square or a rectangle, and the length and the width have to be a power of 2. Here I've identified this large box, which occurs when V5 is equal to 1. And now I've identified this smaller box, which occurs when V3 and V4 are ANDed together. I generate my final signal by ORing together all the signals for the boxes. So we AND V3 and V4 together, and then we OR this with V5 to get our final signal. And here's the logic for this. V3 and V4 are ANDed together, and the end of these two signals is combined with V5 to generate our final V blank signal. Then we repeat this process again for the horizontal blank signal. Through characters 0 through 39, I want the horizontal blank signal to be low. Then from 40 to 64, I want it to be high. Above that, I don't really care, because our beam should never get there. So I'm going to choose this set of 3 boxes to cover all the 1s and exclude all of the 0s. Notice how I had to use the purple and the green box to get those 3 1s in a row. And that's because the boxes can only contain 1, 2, 4, or 8 squares in this case. Again, I can treat an X as either a 1 or a 0, depending on what's most convenient. The bottom signal is easy, that's just HC6. The purple square is HC5 ANDed with HC3. And the green box is HC5 ANDed with HC4. So the final equation for horizontal blank is HC6 ORed with HC5 ANDed with HC3, and also ORed with HC5 ANDed with HC4. Now in Boolean algebra there's a thing called the distributive law, which says I'm allowed to pull out the common HC5 in this part of the equation. Now I know learning the rules of Boolean logic can feel a bit like this.
What's this then? Romanes eunt domus? People call Romanes, they go the house?
It says Romans go home.
No, it doesn't. What's Latin for Roman? Come on, come on.
Romanus?
Goes like.
Annus?
Vocative plural of annus is.
Annie?
Romani.
But it really is worth the effort at some point. So to generate horizontal blank, I OR HC3 and HC4, I AND this signal with HC5, then I OR this signal with HC6. And I end up with this circuit with 2 OR gates and an AND gate. Now I'm getting to the point where I want to start testing this circuit on a monitor. So I need to start combining all these horizontal and vertical signals. So we've generated a vertical sync signal that's active low, which is why it has the bar above it, but our horizontal sync signal is active high. So the first thing I'm going to do is add an inverter to make horizontal sync active low. If I do this, I can just AND these signals together, and I want to run it through a flip-flop to clean it up, and this is our combined sync. Similarly, I can OR H blank and V blank together, and this generates our overall blank signal, and active is just the inverse of blank. create a signal that the monitor can actually use, I need to convert all these digital signals into an analog signal. This is the circuit that Steve Wozniak used in the Apple II, and I'll just go through it quickly. First, we don't need the auxiliary video connector. And we're not going to use colour for now, so we can just tie the colour burst signal low. This circuit's just a resistor-based voltage divider, and this sets the voltages we want for video, for blank, and for sync. And this transistor is set up as an emitter-follower circuit. What does this mean? Well, if we look at the voltage at the base and the voltage at the emitter, the voltage at the emitter is always about 0.6 volts less than the voltage at the base. And obviously it can't go below 0. The reason Woz used this circuit is that it separates the voltage divider from the load on the output cable. So now when I connect up active and composite sync, I should be able to generate a signal that the monitor can lock onto. And there we have it, a signal on a monitor. The white square in the middle is the active area. Then we have the horizontal back porch on the left and the horizontal front porch on the right, which is why I think they're bass-awkward. And similarly, the vertical back porch is up the top and the vertical front porch is down the bottom. Now, I was planning to leave a few minutes to debug this circuit, but it actually worked first go. So, school's out. So this is the end of the video. Please remember to like, subscribe, and share.